Welcome to the Deep Dive. Today we're going on a journey into the world of mathematics, but not the kind you might remember from school. We're not just focusing on rigid proofs and formulas.
Right.
Instead, we're diving into how mathematicians actually, discover things.
Mm. It's like peeking behind the curtain to see that creative process,
Yeah.
the messy but exciting part of mathematical thinking.
Exactly. And our guide for this adventure is George Polya's book, Mathematics and Plausible Reasoning.
Great book.
Polya was a renowned mathematician who believed the journey of discovery was just as important as the destination, the final proof.
Yeah.
We've got excerpts from his preface and various chapters to explore, filled with examples and his own insightful commentary.
I'm excited.
Me too. Our mission today is to give you a glimpse into how mathematicians think. You'll see how they use intuition, analogy, and even what Polya calls, educated guessing to crack open new mathematical ideas.
It's really a different way of thinking about math.
Okay, so let's start with this idea of plausible reasoning. Polya distinguishes it from demonstrative reasoning, which is what most people think of when they think of math.
Right. It's the kind of the more formal side of things.
Right.
He compares demonstrative reasoning to the kind of evidence you'd see in a courtroom or scientific paper. It's the airtight, rock-solid proof, but plausible reasoning. That's the detective work that happens before the case is closed.
So it's more like, I have a hunch, and here's why I think I'm onto something.
Exactly. It's about forming conjectures
Mm.
based on observations, patterns, and even analogies. That might seem a bit far-fetched at first.
I like that.
Yeah.
Polya argues that even in pure mathematics, discovery isn't always this linear, step-by-step process. There's a lot of exploration and experimentation involved.
It can be messy.
Yeah.
A lot of trial and error.
He has this great quote where he says, "We secure our mathematical knowledge by demonstrative reasoning, but we support our conjectures by plausible reasoning. So both are essential, but they play different roles in the process."
And I think that's really key, because sometimes people think of math as just being about the proof, but it's the journey to get there that's often the most exciting.
That's like the difference between presenting your findings at a conference and all the late nights in the lab trying things out and hitting dead ends along the way.
Exactly. And Polya points out that while demonstrative reasoning is crucial for establishing mathematical truths, it's plausible reasoning that leads to the truly groundbreaking new ideas.
That's where the real excitement lies. And speaking of excitement, Polya gives this incredible example of how the famous mathematician Euler used plausible reasoning to tackle a problem about infinite series.
Oh yeah, Euler was a genius.
This was a time when mathematicians were grappling with the concept of infinity, trying to figure out how rules that worked for finite objects could be applied to these vast, unending series.
Right, pushing the boundaries of what was known at the time.
So did Euler just play by the existing rules?
Well, not exactly. He took a bold step and drew an analogy with finite algebraic equations, which, on the surface, seem completely different from infinite series.
Wait, so he compared apples and oranges and it worked?
It's even more daring than that.
Hmm.
He took a rule designed for one specific situation and applied it to a situation where it wasn't meant to be used. It was a leap of faith, guided by analogy.
But it wasn't just a random guess, right? He had some rationale behind this.
Absolutely. His reasoning was rooted in the emerging field of what he called analysis of the infinite. Mathematicians were starting to see these intriguing connections between finite and infinite processes, and Euler was at the forefront of this exploration.
So he was riding this wave of new mathematical thinking and using it to push the boundaries.
Exactly, and through careful observation and tons of examples, Euler noticed this fascinating pattern in how the coefficients of finite equations related to their roots.
Mhm.
And he wondered, could this pattern hold true for infinite series, even though the rules don't technically apply?
So the big question is, did his gamble pay off?
It did. He used this seemingly out there analogy to develop a formula for the sum of an infinite series, a formula that had baffled mathematicians for years. But it wasn't just luck. He then meticulously tested his conjecture using a process called induction.
Okay, so tell me more about this induction process. Is it just about testing, testing, testing?
It's a bit more nuanced than that.
Mm.
It's about systematically verifying a conjecture in a wide range of specific cases. The more cases that fit the pattern, the stronger your confidence in the overall truth of the conjecture.
It's like building a case, brick by brick. Each supporting example strengthens the foundation of your idea.
That's a great analogy. And in Euler's case, he tested his formula in so many cases that he was eventually convinced of its truth, even though he didn't have a formal proof yet.
That's fascinating. But if he didn't have a formal proof, was he really justified in believing his formula? It seems a bit risky.
That's the intriguing thing about plausible reasoning. It's not about absolute certainty. It's about carefully weighing the evidence, considering the analogies, and being willing to take a leap of faith based on the patterns you observe.
It sounds like a delicate balance between intuition and rigorous testing. Now, Polya highlights three key elements that pop up repeatedly in this process of inductive reasoning: generalization, specialization, and analogy.
Think of these as the essential tools in a mathematician's toolkit.
Okay.
Generalization is about taking a specific idea and seeing if it applies to a broader class of objects. Specialization is the opposite, zooming in on a specific case to gain a deeper understanding.
An analogy, as we've seen with Euler, is about finding those unexpected parallels between seemingly different concepts.
Right, and sometimes those analogies can be really surprising.
Well,
I'll use a fantastic example to show how these tools work together. Euclid's classic proof of the Pythagorean theorem.
oh yeah, I remember that one from school. A squared plus b squared equals c squared, but I honestly have no idea how the proof works.
It's beautiful. It's a beautiful illustration of these principles in action. Euclid starts by generalizing the problem, moving from a specific right triangle to the concept of squares constructed on each side.
So he's expanding the scope, looking at the bigger picture.
Then he uses specialization to examine specific relationships within the squares and triangles. And finally, he leverages an analogy between areas to connect all the pieces.
It's like he's taking this abstract theorem and grounding it in something more concrete, the visual relationships between shapes.
Exactly. And that's the power of plausible reasoning. It allows mathematicians to move fluidly between different levels of abstraction, using analogy, generalization, and specialization to build a convincing case.
But as we've seen, plausible reasoning isn't foolproof. Polya also cautions that analogy, while powerful, can sometimes lead us down the wrong path.
It's a tool. Like any tool, it can be used for good or for, not so good.
Right.
While plausible reasoning can lead to brilliant insights, it's crucial to be aware of its limitations. It doesn't offer the same level of certainty as a formal proof.
So it's a fantastic tool for exploration and discovery, but we need to use it with caution.
Right, and Polya offers this insightful reminder in the book. He stresses that generalizations should be about distilling the essence of an idea, not just diluting it with jargon. That's a valuable lesson for any field, not just mathematics.
Absolutely.
So far, we've been talking about these kind of abstract concepts like infinite series and the Pythagorean theorem, but Polya also shows how plausible reasoning can be applied to, more hands-on visual problems.
He uses the example of Euler's formula for polyhedra to illustrate how inductive reasoning works in geometry.
Refresh my memory. What is Euler's formula again? It's been a while since geometry class.
It's a surprisingly simple but profound relationship between the number of faces, vertices, and edges of any convex polyhedron. It states that the number of faces, f, plus the number of vertices, v, equals the number of edges, e plus 2, f plus v plus 2.
Okay, I remember seeing that before. So if I think about a cube, it has 6 faces, 8 vertices, and 12 edges. And sure enough, 6 plus 8 equals 12 plus 2. It works. Exactly. And the remarkable thing is that this formula holds true for any convex polyhedron, no matter how complex.
But how did Euler arrive at this formula? Did he just stumble upon it by chance?
This is where inductive reasoning shines. Polya encourages you, the listener, to imagine yourself as a mathematician exploring this problem for the first time. You might start by examining a variety of polyhedra cubes, pyramids, prisms, and so on, and carefully counting their faces, vertices, and edges.
So it's back to that hands-on approach we discussed earlier, building your understanding through observation and experimentation.
Precisely. And as you gather more and more data, you'd start to notice this intriguing pattern emerging. The sum of the faces and vertices consistently exceeds the number of edges by 2.
Okay, I'm starting to see it. But we can't possibly test every single polyhedron out there. How do we go from these specific observations to a general rule that we believe holds true for all cases?
Polya describes a clever way to extend your testing. He suggests imagining that you're building more complex polyhedra by adding roofs to existing ones.
Okay, so let's say we start with a simple cube. Then we add a pyramid-shaped roof on top of one of the faces.
Exactly. And as you add each roof, you meticulously keep track of how the number of faces, vertices, and edges changes. What you'd find is that with each additional roof, Euler's formula continues to hold true.
That reminds me of those proof by induction problems we did in math class, where you show that if something works for a base case and it keeps working as you incrementally increase the size, then it must work for all cases.
That's the underlying principle at play here. But there's a fascinating distinction between how mathematicians and, say, naturalists approach inductive reasoning.
Wait, what do naturalists have to do with mathematics?
Polya draws a thought-provoking parallel between these two fields. He points out that both naturalists and mathematicians use inductive reasoning to develop conjectures based on their observations. But mathematicians take it a step further. They're constantly seeking to disprove their conjectures.
So they're not just looking for evidence that supports their ideas. They're actively trying to find cases where their ideas break down.
Exactly. This rigorous, almost adversarial testing is what helps refine and solidify mathematical knowledge. It's a key part of what sets mathematics apart from purely empirical fields.
It's like the scientific method, but with this added layer of skepticism built in. Always questioning, always pushing the boundaries of what you think you know.
Now let's shift gears and delve into the fascinating world of number theory. Polya shows how inductive reasoning can help us uncover hidden relationships between numbers.
I love those aha moments when you see an unexpected connection between numbers that seem totally unrelated.
He starts with a classic problem, finding right triangles where all three sides have integer lengths. These are the famous Pythagorean triples.
Right, like the 3-4-5 right triangle.
Exactly. Polya leads the listener through a thought experiment. He suggests making a table of odd prime numbers and seeing if any of them can be the hypotenuse of a right triangle with integer sides.
So for each prime number, we try to find two smaller integers that, when squared and added together, equal the square of that prime number.
You got it. And as you go through this process, you start to see these interesting patterns emerging. Some prime numbers, like 5, 13, and 17, work beautifully. But others, like 3, 7, and 11, just don't seem to fit the bill.
So the natural question is there a rule that governs which prime numbers can be the hypotenuse of these special right triangles?
And this is where the power of inductive reasoning comes in. By carefully observing the patterns and making well-informed conjectures, we can start to unravel the underlying structure at play.
It can't be a super simple rule, or we would have figured it out ages ago.
You're right. It's not immediately obvious. But then Polya introduces a seemingly unrelated concept, the number of ways to represent a given number as the sum of four odd squares.
Hold on, how are triangles connected to sums of squares? This is where I get lost.
That's the beauty of it. Sometimes the most unexpected connections lead to the most profound insights. Polya shows this mind-blowing link between the number of representations of a number as the sum of four odd squares and the sum of its divisors.
Divisors. As in, the numbers that divide evenly into a given number. I'm still trying to wrap my head around how those fit into all of this.
It's one of those connections that highlights the remarkable interconnectedness of mathematical concepts. And it's through this process of carefully observing patterns, making conjectures, and testing them out in specific cases that we can uncover these hidden relationships.
I'm starting to see how this whole inductive process works. It's like being a detective. You gather evidence, look for patterns, make a guess, and then test that guess relentlessly.
That's a fantastic analogy. And like any good detective, mathematicians need to be meticulous in their observations and cautious in their conclusions.
Polya really emphasizes the importance of making very precise predictions when testing conjectures.
He makes a brilliant point about the weight of evidence. Verifying a precise prediction carries far more weight than just a general confirmation. If you can accurately predict the exact outcome in a specific case, it significantly strengthens your belief in the underlying principle.
It's like the difference between saying, I think it might rain tomorrow, and saying, I predict there will be exactly 2.5 inches of rain between 3 p.m. and 5 p.m. tomorrow. If you get that second prediction right, it's pretty impressive.
Precisely. And that level of precision is what sets mathematical induction apart from more general forms of inductive reasoning.
So we've seen how powerful this plausible reasoning can be, but what about the times when it leads us down the wrong path, when our intuition fails us?
Well, Polya doesn't shy away from those examples. In fact, he uses them to highlight the importance of constantly testing and refining our conjectures. He has a whole section called Further Kinds of Plausible Reasons, and it's full of cautionary tales.
So give us an example. When does this plausible reasoning go off the rails?
One example he gives is this heuristic principle, that systems of equations with as many equations as unknowns usually have a solution. Seems pretty logical. You know, if you have enough pieces of the puzzle, you should be able to figure out the missing values.
Yeah, that makes intuitive sense. Where's the catch?
Polya provides a clever counterexample where this principle breaks down. It involves determinants, which are a bit more technical. But the key takeaway is that even these seemingly reliable heuristics aren't foolproof. We can't just blindly accept them.
So even seasoned mathematicians can get tripped up by these principles.
It happens to the best of us. And it highlights the importance of always approaching these principles with a healthy dose of skepticism. They're useful tools, but they're not substitutes for rigorous testing and analysis.
Okay, we need to be careful about relying too heavily on heuristics. What about a more real-world example of plausible reasoning leading to a dead end?
Polya dives into a fascinating historical example, Johannes Kepler's quest to connect planetary distances to the five Platonic solids. Those perfectly symmetrical shapes we talked about earlier, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron.
Ah, yes, those beautiful geometric figures. I vaguely remember them from geometry class.
Kepler was obsessed with these shapes. He believed their perfection must be reflected in the structure of the universe.
So he was trying to build a mathematical model that linked these shapes to the orbits of the planets.
Exactly. He envisioned these Platonic solids nested inside each other, with their dimensions corresponding to the distances between the planets. You can see how visually compelling this idea is.
I can see the appeal, but it also sounds a bit like trying to fit square pegs into round holes. Did it work?
Not really. As Polya points out, the agreement between Kepler's model and the actual observed data was weak. But Kepler was so convinced by the beauty and symmetry of his idea that he kept tweaking and refining it, trying to force it to fit the evidence.
It's like that confirmation bias we all experience sometimes. We see what we want to see, even if the evidence points us in another direction.
And it shows the allure of plausible reasoning. These ideas can be so elegant, so aesthetically pleasing, that we might cling to them even when they don't match reality.
But hold on,
But
didn't Kepler's work on planetary motion eventually lead to major breakthroughs, even if this particular idea was a dead end?
absolutely. And this is a crucial point that Polya makes. Even when plausible reasoning leads us down the wrong path, the process itself can be incredibly valuable.
So it's not just about being right or wrong. It's about the exploration, the journey of discovery itself.
Exactly. Kepler's quest, although ultimately flawed, laid the groundwork for his later groundbreaking work.
Mm.
His willingness to make bold conjectures and test them rigorously helped to revolutionize our understanding of the universe.
And that reminds me of something Polya said, that no idea is really bad.
He's encouraging us to embrace the messiness of the creative process, to be willing to guess, even if those guesses turn out to be wrong. It's often in those missteps that we find the path to truly innovative insights.
This has been fascinating, but let's bring it back down to earth for a moment. How can we, the non-mathematicians, use these ideas in our own lives?
Well, Polya's insights are relevant to anyone who wants to understand the world better. He reminds us that the process of discovery is just as important as the end result. That analogy, generalization, and specialization are powerful tools for exploring complex ideas, no matter what field you're in.
And that it's okay to make educated guesses, to be willing to be wrong, to revise our thinking as we learn more.
Polya ends his book with this wonderful call to action. Be cautiously optimistic when testing your guesses. He's basically saying, go explore, be curious, be bold, and don't be afraid to follow your intuition. You might be amazed by what you discover.
So the next time you face a challenging problem, remember Euler and his daring analogies. Remember Kepler and his cosmic quest. Embrace the power of plausible reasoning.
Who knows, you might just have your own aha moment.
And that's a wrap for our deep dive into the world of mathematical thinking. Thanks for joining us.